Okay, hi everyone. Here that's live people for the second section of Quantum T and people that is watching YouTube. You guys are really welcome. So my idea today is to present to you guys some slides just to give some pedagogical things, a little bit about just a summary about like the Copenhagen interpretation and make an example about the uh, a very someone who wrote uh, and have one example about the double slit experience. And we make some calculations, but very brief. I intend to do this in like 15 minutes or 20 minutes, and then I open the section to discussion. And you guys are free, like to choose the need to follow. It's just to I just like to show some these things because maybe some people in the audience is not familiar with this quantum thing. So just to give a brief introduction. So I'll start like sharing my slides. Okay. Okay, so sorry about that. This is the slides. So it's the quantum key. This is our logo that was like made for artificial intelligence. And okay, that's start. The for the this meeting today, I will just give a brief about the Copenhagen interpretation. Like first, I'll say something about the idea behind this round table style of meeting, quantum T, and then just a summary about the Copenhagen interpretation, just for people that is not familiar. And then I'll give an example, the double slit example, and we'll be open for discussion. So, okay. So the idea behind that we have when we like decide to create this round table style of meeting series of lectures uh, is to discuss like the different quantum mechanics interpretations. So in principle, I will always like bring some, let's say, topic, and from this topic, when I show like the slides, we open for the discussion, so we can discuss not only the things related to the slides. I mean, the slides is just to people that's not familiar, but when we start the discussion, the things are you guys are free like to discuss the topics you want. So this is the idea. And as examples, I mean, this is just a brief abstract. I'll start like today, maybe in the next couple of meetings that when we schedule. I'll talk about the Copenhagen interpretations, and then after that, we'll show some, not necessarily in this order. I mean, we can like jump some of them or, or invert the order. There is no problem. But this is just to give an idea that, at least in principle, the things that I have. Talk about the famous EPR paradox, the Einstein-Podolsky-Rosen, that question the completeness of quantum mechanics. And then the Bell inequalities was proposed by John Bell in the 60s. This is from the 30s. Maybe discuss a little bit about the Schrödinger and his famous cat paradox that treats the problems of interference for macroscopic objects. And then some different interpretations, like the Bohm, sometimes called Bohm the Broglie interpretation, who proposes a non-local theory of hidden variables. The Everett interpretation that's related to the main world interpretation from the 50s, I think late 50s. And other types, like maybe not so famous, but spontaneous collapses theories, like this Girardi, and I forgot the name. GRW is G is from Girardi, the other two guys I forget the names. Models and pairs dynamic model. Another type of interpretation is the consistent histories, that's proposing in principle by Gelman and some other collaborators, and many other things and topics that you guys can bring and we can discuss. Like I think that in the last meeting, I think it was Diego who proposed to one day we have like a discussion about the Dodge proposal from propose the experiment to using quantum computing for differentiate like the many world interpretation in the Copenhagen. That this is a thing that we can like do in the future. I mean, it's very interesting. So this is the idea, initial idea, but I mean the things can change, and then we don't have to follow these settings. Okay, so a little bit about Copenhagen interpretation is just this is just a summary, okay, just to people that is not use it, so to have to something like to start some idea, basic idea. So the expression initially, the expression Copenhagen interpretation refers to the large influence of Niels Bohr in the comprehension of quantum mechanics. So Niels Bohr is a Danish physicist from the he born, I think, in 1895, but was his first, maybe his first important work paper was from, I think, 1911, related to the atomic rules, the famous Bohr atoms that could explain before the theory of quantum mechanics be complete. We could explain some experimental results from the hydrogen atom using some postulates that Bohr decided. And then during the comprehension of quantum mechanics, when the theory was like complete in the late 20s, he influential was very big, I mean, in the interpretation of quantum mechanics, and that's why this type of interpretation, that's the most till today is the most famous, the most like adopted in the textbook, quantum mechanics textbooks. That's why it's known as Copenhagen interpretation. So this interpretation gets a common view related to indeterminism, discreteness, and divisibility of nature, as well as the absence of causality and the idea that the goal of science is not to understand nature how it is, but just to understand what we can get when doing experiments. So this is the Niels Bohr words. I forgot to put the reference here, but in the end I have this. I put some reference. So Niels Bohr says there is no quantum world. There is only an abstract physical description. It's wrong to think that the task of physics is to find how nature is. Physics concerns what we can say about nature. So this is the very brief. And following from Bohr, we have another important physicist like Heisenberg, Max Born, that was the first to give the interpretation, probabilistic interpretation of the wave function. Wolfgang Pauli and many others. All these guys are adapt from the philosophical current of thinkers named positivism, whose main founders are people like Immanuel Kant, Hume, Mach, etc. In summary, for this group of thinkers, the only way to get knowledge is by the scientific method. And in a more radical formulation called idealism, that like positivism is a soft type, let's say, from this. Even the scientific method is superfluous, like to understand the nature. And the reason is because, like, since all observation is given by our senses, science is just a logical consequence of human experience. Thus, the idea of an existence of reality independent of human perception can never be tested for us, since it will always have intermediation of our senses. So this is just a brief summary. So, given these philosophical premises, the idea behind the Copenhagen interpretation, defenders about quantum phenomena, can be summarized in this way. But here, only three topics. Like the quantum phenomena are random, unpredictable, and unique. It's not possible to give any properties to a quantum particle before these properties are observed. Certain quantum particle properties can not coexist, and when we try to introduce a new property, old properties introduced previously can be destroyed. Well, we can like discuss this in the end, okay? So, but this is related with the uncertainty principle, Heisenberg uncertainty principle, this third topic. So the conclusion is that it's not possible to attribute state of reality for quantum particles independent of human observation. So how to describe the quantum processes and connect them with the reality of facts, I mean, with the experience. So the answer was given by a hard work of brilliant scientists, and especially like physicists and mathematicians. And the result of these ideas was summarized in physical postulates proposed by von Neumann. And just observation that is the list that I'll show now is not consensual, even among the Copenhagen interpretation supporters, and much less when you consider other interpretation defenses. So just a brief summary about the postulates. I'll not give details about them. If you guys want more details, I give in the quantum hardware course, before we start the quantum hardware part, quantum computation part, I give 2 lectures that I give more details about these postulates, that the postulates was proposed by John for von Neumann. So the postulates are basically any one of them, any state of a quantum system at a time t0 is characterized by a vector that we call cat, given like this, that belongs to the Hilbert space. This vector in Hilbert space describes completely the physical state of the system. Everything that can be said about the system is contained in psi, this cat psi. Every measurable physical quantity is described by a self-adjoint operator, or observable, acting in a Hilbert space of the system. Now that is the only possible result of measurement of a physical quantity is one of the eigenvalues of the self-adjoint operator associated with it. And the probability of find one of the eigenvalues, for example, eigenvalue AN, associated with the observed quantity, is given by, in the case of discrete case, we can also have the continuous case, but here I'm showing only the discrete case. It's given by this. So this P here is the probability, and is given them from this expression, where this Pn here is the projector of the eigensubspace of the Hilbert space with eigenvalue An. And this Un here is one of the eigenstates with eigenvalue with degeneracy. Gn is the degree of degeneracy of the system. Okay, so this is the probability given this way. After the measurement generated the eigenvalue An, the state of the system collapses for psi prime here, given by this expression like this. This term here is just to to normalize. And the last, I mean, I divide in 6 postulates, but it's not consensual. It's like the von Neumann style to introduce quantum mechanics. So the last is like the evolution of the state vector while no experiments are carried out is governed by the Schrödinger equation, where h of t is the Hamiltonian operator of the system. We can also write this, like describe this in terms of the what's called the Heisenberg description. That's given this way. The difference is like the the observables, are time dependent, and the state is constant. In the Schrödinger description, the state is time dependent. But I mean, both are equivalent. There's no, just in general, the Schrödinger is, when you're solving like the problems for quantum mechanics, is in general this is much easier to solve using the Schrödinger description. Okay, so these are the basic postulates, and just an example, and we can use is like the famous double slit experiment. I think most of you guys know about, but you can consider like in an experiment like this, like a source. This source could be a source of light or electrons. I will say here, like, I mean, electrons or atoms or even molecules. Some people today, people can make an experiment using this. I will always refer to this experiment here from electrons, okay? Because I think it's better than using light, because the effect will be more impressive maybe. So if you consider like a set of electrons being sent in the source, one by one. So if you will like close one slit and let only one open, like in this first case, what I'm calling like the right slit, only this slit is open. So what you observe, you will observe a thing like that. That is related with the classical theory or the particle theory, is it here? Okay, so this is like a particle behavior. The same thing would happen if you close the right slit and open the left slit. The only difference that is the what we observe will be dislocated to the other side. But again, it's like a particle theory observation. But if you open both slits, so what you observe is this. So you have a wave observation. So according to the Copenhagen interpretation, the electrons behave like waves, like they went like spread out on the both slits. So this is the wave particle duality, right? So just to use like the math a little bit, just so we understand, it's just few calculations. Let me show here. Let me show you what we have. We try to understand. Okay. So in the double slit, experiment. So if you let's use the postulates. And again, this postulate is according to the Copenhagen interpretation. Let's use the postulates to describe the double slit experiment. So initially, we have the state psi for one electron, okay? When I'm saying electron, again, could be like photon, an atom, or whatever. And in the double slit experiment, the state psi is given by psi1 plus psi2. Psi1 psi2. So this state corresponds to the two possibilities. And in this case, the electron goes for slit 1 or by slit 2. And using the postulates, we can find like the probability density that I call like P of x for the electron. In the position, the probability density P of x for the electron in the position x. So, using the postulates, P of x is just x, the projector P, in this case a px, because the only possibility for n is x, of x, sorry, psi. If you use the definition of the probability, or the probability, the projector, P is just P of x is just like x. So if you use this here, we will have psi x psi, which is just this is the psi. This is the conjugate, and this is the psi. So we have the expression for the probability, which is just, this is just the psi of x squared. Okay. And from this, let's call this one, from 1 can like multiply for the bra x, x psi is the same of x psi 1 plus psi 2, which gives the psi of x, psi 1 of x plus psi 2 of x. Okay. So the probability p p of x, this probability is just psi conjugate, which is this guy here, conjugate psi 1 of x plus psi 2 of x conjugate. Okay. So this times psi plus. And in the end, just make this sum here. The probability will be just psi of x squared plus psi 2 of x squared plus 2 times the real part of psi 1 conjugate psi. Okay. So this is probability. That's this expression. So this, just to finish, the third term is responsible for the interference when both slits are open. When both slits are open. So in the first case, like when just one slit is open, let's say the right, so psi 1, we should call this psi r and psi l, but okay. When just one slit is open, let's say the right slit, so let's say I'll call this right, which is better, right and left. Right and left. And same here, okay? This right, left, and so on. I'll fix when I give this available. So when only one is open, let's say when the right slit is open, so the left slit is closed, so we don't have this probability, 0. And we don't have the interference part. So the probability will be like only to find the part in the right slit. It's in the first experiment. The same for the second. And when both is open, so we have this interference and the wave interpretation. It's okay. It's just to be like quick. And it's just like an example for people that's not used it with this quantum mechanics things. But I think most of you guys know about this. But okay, now the room now is open for this discussion.
So something has always bothered me about the double slit experiment, and I feel very naive in asking this question. But I'm having trouble envisioning a situation in which you have two slits that are so small that you don't know which one an electron has gone through. Again, this is really a naive sort of, if you imagine shooting an electron and how tiny that is, how can you shoot it in a way that it's not targeted toward one of the two slits? The two slits have to be incredibly small and incredibly close to one another. And how do the physicists manage that? I've seen YouTube videos where you can do the double slit experiment yourself using a human hair or something like that. But human hair is extremely large compared with the sizes that you probably have to get to perform a double slit experiment. I know that I'm not seeing this correctly. When I must definitely be making analogies that I shouldn't be making in order to have this problem, but it's been bothering me for approximately 50 or so years, and I've never articulated it before. Congratulations, you're the first. Is my question or concern clear in any way?
Yeah, I'm trying to understand. So you have the two slits, because in general is you have like the two slits, the traditional experiment.
Yep.
You have like the two slits, and the separation of the slits is much bigger than the electron size. Okay.
Right.
So the question when people ask, oh, how this could have like a wave interpretation, how they could interfere if the electrons are so small and the distance between the slits is much bigger, how we could like have a wave interpretation about this. So this is the question since like Einstein make these things. But I think what I say is a little bit different, right? If I understand, you have the two slits much closer. Maybe, see if someone understood better than me, you can like say something.
So here's the electron coming toward the double slit barrier, and here are the slits like this. Okay, now unless you have very sloppy trajectory of the electron, you know that it's either going to hit the barrier and not go anywhere, not go through, or that it's going to go through this slit or that slit, right? Now, I can imagine you're not knowing which slit it goes through, but in that case, these slits have to be very, 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 very close to one another, and the narrow barrier between them has to be. I mean, we're talking about an electron. An electron is tiny, so the barrier between them has to be, I'm imagining, very, very tiny, maybe even electron-sized, which is very difficult to pull off in a laboratory, I would imagine. Why then am I reading? Why are all the explanations of this so casual about the engineering involved in making the slits so close to one another that it's not clear which electron they're going through? Why is it that I can look on YouTube and see an experiment that seems to indicate that the distance between the slits can be as large as a human hair? Certainly, a human hair is so large compared to an electron that an electron is going to be on one side of it or the other, unless the wave of the electron is larger than the width of a human hair, which the answer, the response to this.
Yeah, that's the at least for Copenhagen interpretations, when you have this wave duality, that the wave from the electron is bigger and you can interfere in the end. Yes, this. But
So,
this is the Copenhagen interpretation. So this is the wave probability for the electron. I think Diego wants to complement something. Please, Diego.
Yeah, I think that is the point of the experiment, is to show that electrons aren't really localized particles. So electrons are actually waves of probabilities. Now, we are used to seeing them as localized particles because when we interact with them, we localize them in a specific spot. But in this experiment, the electron is a wave propagating with some wavelength. I mean, if you've been following the videos that Carlos has put up on the quantum hardware explanations, you can prepare, for example, a wave packet, right? And that wave packet has some wavelength, but that wavelength is larger than the separation between the slits. So it's always a wave propagating. Now, when you measure it, what happens is that, this wave packet is like a Gaussian distribution with some, oscillatory terms. When you perform a measurement, that Gaussian actually narrows down. And the resolution of how much it narrows down depends on the wavelength of the photons you're using to perform the measurement. But it's never a single small spot. It's always a wave, right? And again, this is the Copenhagen interpretation. But even if you think about pile wave theory, where the idea is that you do have one particle, well, the guiding wave in pile wave theory is also a wave propagating that is going to interfere with itself. So the details of how you do this in an experimental setup is you prepare the electrons to have a wavelength that is going to be larger than the separation between the slits.
Okay, and you can prepare an electron with a particular wavelength?
You typically prepare them in the form of a wave packet. But yes, it depends on the energy. So that's given by, the frequency energy relationship. So you could have different wavelengths. Yeah.
Okay. All right.
I mean, forget about, for example, the electron and think about a photon, right? A photon can have different wavelengths, and you can prepare also. Photons a little bit more complicated because it's quantization of the electromagnetic field. But I mean, you can prepare in a certain wavelength and send it through a double slit experiment and cause that interference.
That actually, I'm glad I asked. I am sincere in saying that I have more insight now than I did before I asked the question. Thank you.
Yeah.
Sometimes I lie about that and say, yeah, I understood, and I really didn't, but this time I did.
Good.
The real question when it comes to interpretation is, what is this wave made of, though? Right?
Yeah.
That's the problem, right? Because it's not an electromagnetic wave, it's not an electrical wave, right? It's a wave of probability. So that's the part that gets tricky.
Bob raised his hand. Oh, I think you moved.
Got it. You hear me now? Yes. Good. Basically, Barry, another way to look at this is we're talking about the size of the slit. And you keep saying the size of the electron. Really what you're looking at is the size of the amplitude of the wave.
Right.
Versus the size of the slit.
Yeah.
Because a lot of times with these slit experiments, when something passes through the slit, the ones that don't touch the edge of the slit are unaffected. They don't even know the slit's there. It's the pieces that touch the very edge of the slit where the scattering happens. And that's where you get the odd behavior. Right? And that, whether or not they're going to touch the edge of that slit, intuitively is based on the amplitude of the wave.
Right. Yeah, no, I wasn't thinking of the amplitude of the wave being that.
Right. You're thinking the scale of the electron, the amplitude might be much larger than the electron itself.
Yeah.
Just like the wavelength will be much larger than the electron itself.
In the meantime, I've tried doing what they suggest in these YouTube videos. Doesn't work for me.
And you know what happens is that's the idea that that's really what you're proving, because if the electron was a particle, then the only effect you'd really be worried about, the slit size that relates to the size of the electron.
Right.
Because it's maybe the wave of slit size and separation is related to the wavelength and the amplitudes. It's almost like an intuitive thing.
Got it.
Great.
Thank you.
You're welcome.
And this question is not naive, because this is one of the questions that Einstein was like asking in the Bohr debates. Of how
When Einstein asks it, it's not naive. When I ask it, it is. There's a difference.
Well, I have a naive question. This is definitely naive.
it's the hardest question of the naive questions. Okay, Mohammed, go ahead.
Okay, so my question is, what does Copenhagen interpretation says about? Okay, electrons are very small. Like we don't really experience them in our daily lives, right? What if we run, instead of electron, let's create a double slit with the tennis balls? What does the double slit say about that? I mean, sorry, the Copenhagen interpretation.
Well, because a tennis ball, they like lose these quantum properties. What Bohr described as the complementary principle. So basically, when you have like microscopic things, big things, so you lose these properties, and you can see this weird behavior that you see in small world. But this, I think Diego wants to say something.
Yeah, no, I just wanted to. So what you are saying is the Copenhagen interpretation then, like, some sort of splits the world into the world of the large objects that these effects are more obviously observed, and the world of the smaller object where these phenomena manifest, or at least our experiments can detect them.
Yeah, but the thing is that this limit is not well defined. You don't know what's this limit. I mean, by the time in the beginning of the quantum theory, we make the experiments with electrons. But today you can do some experiments using some molecules. There's some big atoms and some molecules. You can do like these experiments. So what is the limit? The theories don't know. That's the thing.
Is this the limit of our experimental capabilities of our instruments, or something else?
That's the question. That's the question. If there is this difference of the words, like in the principle Copenhagen interpretation is saying, or this is just something that this is what we can measure, but we don't know when this will stop. When they think we can make the experiments with larger and larger things that we are doing today, because the advance of the technology. So when this is stopped, this is the question. We don't know the answer. And people, I know some people that are trying to see some quantum properties. I don't know about some. I know with using some virus, which would be very interesting if you could do it. Virus, and then if you could make with bacteria, because bacteria is alive in being. So this would be like very impressive. But I mean, till I know today, currently, we still don't know non-result with virus. But I mean, that's the question. I don't know the answer.
There have been double slit experiments with buckyballs. So buckyballs are larger molecule. Well, yeah, it's like a carbon molecules, which are, relatively large in size, and you can start seeing the interference effects. So they do behave like waves. But I think the problem is that as you keep increasing the size of the object, the chances of it interacting with its environment, it's larger. So it decoheres. So it loses its quantum properties a lot faster. I think that's the challenge.
I wonder if this is an issue of scale, in the sense that we can see these phenomena on, let's say, a very small item, an electron, a buckyball, a virus, or whatever. Because we're so much larger than it, and we're observing it. Partly what Diego said about the quantity of items is huge compared to what we compare. And that we would not see this, let's say, this phenomena on a tennis ball, because we're not far enough away in scale to observe it the way we need to observe it to see the phenomena. Because we'd never have a billion tennis balls interacting. That just the observation part, we have to be separated by a certain scale from the thing we're observing. Well, no, it's just speculation, but.
Yeah, this is an open question. As I said, we don't know the limit. Probably it's because Diego said, I mean, the interaction of the big particle with the environment could make they lose these quantum properties. But this is open question. We're not sure about this. But I mean, what say like, is there this difference, a quantum world and a classical world, or is just something? It's like the same thing, but the thing is, the thing will decoy. I think this is related with what some people from Copenhagen interpretation.
It's still hard to believe that there are two worlds, a classical and a world. That just rubs my intuitions the wrong way.
Maybe,
I agree.
Yeah, maybe this is just a comment, a naive comment again. It could be like we feel hard with quantum mechanics because we learn classical mechanics. We can imagine a civilization somewhere in the universe. They started, maybe they discovered quantum mechanics first. In that case, maybe they didn't need even to go to classical mechanics. They could explain everything. And this type of thing wouldn't probably be a problem for them, I guess.
And Andre, as interaction with environment has to be electromagnetic. Not necessarily. It could be like even like fluctuations of temperature. If there is some type of special fluids called superfluids, like a Bose-Einstein condensate, that you can make the molecules that come out of the fluid to have like a quantum properties. It's like a type of quantum fluid, and you are able to do that only with very low temperature, and close to zero Kelvin, like something to 10. I don't remember exactly. 10 to the minus 6, 7 Kelvin, something like this. So, little fluctuations in the temperature, in the environment, would make the particles to make you lose the quantum properties. Someone want?
Yeah, go ahead.
Diego.
No, I just wanted to make the comment that this discussion about having two separate worlds between, what is the quantum or what is the classical, I think it speaks of the issue with the Copenhagen interpretation, that you need to have two separate dynamical laws to explain when you're having interference and when you're having a measurement, right? But the problem is, what part of a physical system causes that divide, right? If your measurement instrument is also made of, atoms and molecules, why do we treat it differently, right? That's the biggest problem with, the Copenhagen interpretation. So that's why some people recently have been more aligned with the many worlds interpretation or the Everettian interpretation, where everything is just entanglement, right? Even measurements are just entanglement. You just have a single wave function that describes the whole universe. And there's no such thing as collapse. There's no such thing as a measurement. You're just getting entangled with everything around you. But I mean, of course, there's problems with that interpretation. Like if everything is unitary, if all evolutions are unitary, how do you explain probabilities, right? Why do you get this, statistical results when you perform what we perceive as measurements? And there's, a lot of discussion of different ways to interpret that, but it gets really complicated very quickly. So, but yeah, I mean, that divide, where do you put the line, right? And I think von Neumann used to talk about it like there's no place where you can place that cut, right?
I have a follow-up naive question on that, Carlos. What is the take on the what's this the money worlds? What would be the explanation? How would they deal with the double slit experiment?
Well, I'm not so familiar with the
Or anyone who's familiar with that interpretation, what would they say that happened?
Yeah, I can give in principle at least the things that I never really studied in detail, but what I understand when you say, when Copenhagen interpretation say that the wave function collapsed in some of the states, the main words say that you have like a type of split. I mean, you have something that you measure here, but the other possibilities was in a different world, in different universe, you can say. At least, I mean, naively, what I can say is about that. But the thing that when I'll talk about in the future, I will talk about the many world interpretation. But I think Diego is more.
Okay.
So the first portion of the experiment is identical. So you still treat it as a probability wave that interferes with itself through the slits and reaches the screen. So at that point, there's absolutely no difference between Copenhagen and many worlds. Where they differ is when you perform a measurement. So the measurement happens when that wave reaches the screen and you see it localized in one particular spot, right? In Copenhagen interpretation, you said the whole wave function just collapsed into a single point instantaneously, which has problems with relativity and all that. But in many worlds, what they say is that now you can imagine that screen dividing up into every single possible place where that wave could have collapsed and getting entangled with the wave function. So then your wave function just increase exponentially. I mean, we'll have to write it down. Actually, it's a lot easier to explain it with maybe spin than with the double slit experiment, because in the double slit experiment you have a continuous wave function where you have many possibilities of where the particle can collapse. With spin, it's just two options, but the idea is the same, is that let's say you're the measurement apparatus and you get entangled with every single location on the screen. So there will be a version of me that saw the particle collapse on the left. There'll be another version of me that saw it collapse a little bit to the right, and then more to the right, more to the right, more to the right. So there are multiple copies of me, but it's all in a single wave function. Now, that's the problem. Like, I don't feel like I got entangled. How can I explain this, right? And then you say, well, if we're all made out of particles, then all it is that in a version of you, you have, atoms in your body that are pointing one direction. In another version of you, they're pointing in a different direction, but you're all entangled, right? You only believe in one of these experiences, so you only perceive one of these experiences. But the question is, well, why am I perceiving this one and not that other one? Right? So it gets complicated.
Bob, please.
Thank you.
Are you on mute?
Yeah, I got a question about the many worlds interpretation. Does that mean that the version of you, Diego, that's in another world runs the experiment, sees a different pattern, and gets a totally different result, possibly a different conclusion? So in some other world, the double slit experiment says the electron's a particle.
Well, not really. It's easier if you think about it with spin. So let's say you have a particle that you put in a superposition, spin up, spin down, and you send it through a Stern-Gerlach apparatus that it's going to, make the particle deflect up or down, right, with equal probability. So I start the experiment, I perform the experiment, and then when the measurement happens, or when I get entangled with the electron, then there's a version of me that sees it spin up, and there's another version of me that sees it spin down. So the experiment happened just like you perceive it if it would have collapsed, but there's just another version of me that saw the other result.
Right. And I guess what I'm saying is the other result could lead to different conclusions about how the world works.
Oh, yeah. So that's one of the problems with many worlds interpretation, that there's always a version of you. Let's say that you have a particle that is, 99% spin up and 1% spin down. And you repeat that experiment over and over and over and over again. There's always a version of you that always sees it spin down, even though the probability should be 99% to see it spin up. So then that violates, the whole concept of probability amplitudes in a wave function. So that version of me that always sees that 1% spin down says, oh, I always see 100% spin down, even though I prepare it to be 99% spin up. So quantum mechanics doesn't work at all. And what believers in the many worlds interpretation say about that is, well, too bad for that version of me. The version, because these are probabilities, there will be always more versions of me that see how these things should behave. But I don't know. I mean, that's, it's difficult to agree with it, right?
We have a question. Muhammad Reza. He say, also, wouldn't the direction of entropy in force measurements, perhaps resolving the measurement paradox, necessitates a deep understanding of entropy? The direction of entropy in force measurements. Yeah. that's the thing. I mean, entropy is not. There is some debate what exactly it means with entropy, especially when you relate these things with like gravity, because we know like in general entropy is related with the volume of the systems, and when you are considering like a black hole, the entropy is related with the area of the black hole, and this is like a situation. And some people try to understand this as the holographic principle. That like the universe we live was like a holographic universe and so on. But that's the thing. The entropy is not a really well understood constituent. Some other comments. People that writing questions, no problem. But if you guys want to like open the microphone and asking, there is no problem as well. But I mean, I can read, no problem. Abderrahim, sorry if I'm not pronouncing well. He asking, in many words, can virtues of someone or something communicate between them? In principle, at least at my knowledge, no, it cannot. But I think Diego, you are more.
Yeah, that's a difficult question. I think it depends on. There's also different versions or interpretations of the many worlds interpretation. So, in principle, no, because in some versions, what they say is that this split happens when you have interacted with so many other particles and systems that you're so decohered that you can't interact with that branch of the wave function anymore. It's too hard to make that process reversible to interfere again the two versions of that wave function. But this was what I had proposed last week. In what David Deutsch believes, there is a way in which you could, in theory, make those two branches come back and interfere with each other. But then you can't have them decohere. There needs to still be enough coherence for them to branch back together. And that is one of the experiments he had proposed to verify if many worlds is true or if collapse theories are true. It's a little bit complicated because it has to do with what information remains when you interfere them back, what information gets lost. Like, obviously, you can't really communicate, right? But you can perhaps make the wave functions come back and interfere with each other again. I mean, a way to see it is, imagine you have, well, I don't know, did you talk about the Stern-Gerlach experiment in the other course?
Yeah, it's a very, very quick, but yes, related with quantum computing.
Yeah,
yes.
so in Stern-Gerlach, you can have the apparatus and send an electron in an equal superposition, spin down, spin up, right? And then after the apparatus, you have equal probability of it deflecting up and down. You can take two more Stern-Gerlach apparatus and make them make the electron, the wave function of the electron, go back and interfere with itself. So you can think of many worlds as, oh, I've split the worlds into two separate branches, but then I make them interfere with each other again. But that's because that electron remained coherent enough to be able to do that. It didn't interact with the environment to decohere and prevent it from interfering with itself. So you can think of an experiment where you have macroscopic elements, or a large enough of a system where you could split into two worlds, make different things happen, and make them interfere to prove or disprove if this splitting happens or not. But you can come up with an experiment in which, in a collapse theory, this will never happen, but in a many worlds interpretation that would happen. So but again, that's only one version of many worlds. There's others that say you only branch when things have decohered enough. So I don't know. Yeah, it's
In the next lecture, I'm planning to let you show the Stein-Gerlach experiment. But I mean, in the view of the Copenhagen, after that we are open for discussions. And I think George wrote something. George said that maybe each of the many words has a different many words interpretation. Yes, we have infinite interpretations. Okay, so we are almost 1 hour, I think. If you guys want to comments, and also asking about the best way, to we are still looking for the best way to present the restart. My idea is to always give something, 20 minutes, show some slides, make some calculations. If sometimes the calculations are too long, I'll not show the details, but in the end, I think I'll bumble I think I'll let the slides available, so we could look at something, because I will do the calculation, but if sometimes the calculation are too long, I'll always just show the main results, but I like the calculations, everything, if people want to follow. But the live presentation just shows the results when the calculation are too long. But it's not the case today. But yeah, Diego has to leave, and I think we have one. Let's get by Diego. Thank you. George, no. Andre, how many word interpretation practical consequences uses? Yeah, I think it is that thing we are talking. At least what I understand about the many word interpretation is the results we obtain here will be similar with the results, the same as we have from the Copenhagen interpretation. But the things that happens in the other words, at least in principle, unless the example that Diego told us, we cannot see the difference. At least, yeah. The thing I have to say, at least for now, Andre and Diego needs to leave. Bob, I think this format, slides and discussion works well. Okay, Bob. Good. George?
Yeah, I just want to second what Bob said, that I think it's good to ground it in an equation, at least for a little while. Shut up and calculate before getting into the more general discussion.
Yeah.
So we're having both in the T body.
Yeah, it is good. I'll try to be the first 20 minutes was the discussion, and the slides will be available. Okay.
Yeah, I have to run too. Thank you.
Okay, so thanks everyone, and Merry holidays, Merry Christmas, New Year for everyone here.
I just want to. Yeah. Sorry, Carlos. I just wanted to say next. I've scheduled this to be weekly, but next week obviously is Christmas thing. We want New Year's thing. We won't have. So I'll discuss with Carlos, and then you should receive an updated invitation. It won't happen. We won't have Quantum T next Tuesday.
Yeah, next year only.
Only next year. Yeah.
some Thursday next year, in January next year, we still don't know.
Also, I do appreciate you automating the notifications. That makes it much easier.
Yeah, I'll try to do it sooner rather
Yeah.
than like a couple hours. Yeah.
Okay, bye.
Okay, bye. See you guys.
Thank you
Yeah.
very much.
Out.
Good night.
Okay, thanks, Andre.
Good night. Thank you very much. Merry Christmas.
Yeah.
Merry Christmas.
Happy Christmas too. Thank you.
Okay,
I
I'll
think we
stop.
need to stop recording. Yeah.
Only wish.
Yeah.
Okay, I'm stopping.